record the lectures and last time, and if someone is not able to follow this lecture and maybe he'll decide to go for it later, then we'll have this video, then I'll share as a group message on this Moodle platform. So as I said, first part of today's lecture is the discussion about investigation works and monitoring plan. In the second part, we'll discuss on observational design methods. So first thing you have to bear in mind when discussing about importance of investigation works in construction and designing the highways in landslide area is what will be the magnitude of investigation works. How many boreholes should we perform? How deep should the borehole be? What kind of field tests should we perform? How many soil samples, rock samples we should collect? These are very important information when asking for some input information regarding the construction of highway in landslide areas. Where can we find the information like this? Well, we usually find it in some rule books. Locally here in Bosnia and Herzegovina, we have two available rule books that are used as guidance for defining the magnitude of the investigation works. The first one is so-called rule book on geotechnical investigation works and testings from 2009. It's available online, and plenty of information can be found also, although it's only on local language. When you look at the most important questions regarding this, and that's the number of boreholes or borehole spacing, you will not find a lot in this document. Actually, you'll find that the spacing between the boreholes, for highways, railways, channels, pipelines, tunnels, and similar so-called line structures, it says that it has to be minimum spacing must be 20 meters and maximum spacing must be 200 meters. That means if you have an embankment like this, that is 200-meter long, then you should perform one borehole here, one borehole at the end, and you'll have 200-meter spacing of the boreholes. If you have some viaducts, bridges, then you need to have at least two boreholes per every foundation of this viaduct. That's minimum. The maximum stands for 6 boreholes. What we usually do is practice is at least these 2 boreholes before the main design is constructed. As you see, nobody mentioning landslides in this rule book. What happens when we have a landslide area, when we need to construct the highway in the landslide area? Well, some useful information we'll share later in this presentation regarding the concept of investigation works for a construction in the landslide. The other document is the rule book on technical norms for the foundation of buildings from 1988, and that's ex-Yugoslavia standard that is also used. And if you look at it, you'll see that it's practically all the same as the information in this new rule book locally used. And it's also for line structures 20 to 200 meters spacing for the boreholes. And you also have the other part of the rule book saying what should be the spacing between the boreholes if you are constructing some foundation, a large foundation. As for example, you have foundation that is 40 by 40. Then it says you must have at least 4 or 5 boreholes so that the grid formed by those boreholes should be 20 to 30 meters. So this square grid should be with sides of 20 to 30 meters. So that's some range of the borehole spacing that should be performed prior to construction of the buildings on flat area. Of course, still once again, nobody mentioned the landslides. So the landslides are not so much explained in these rule books, and we have to have some experience, some knowledge regarding the problems we can expect, and we have to prepare the investigation work to meet the criteria for the construction in the landslide area. Here is one example of a local highway route that is under construction right now. This is the photography for a few years before, prior to construction of the highway. And here it is defined that this area is an old landslide that could be activated during the construction of the highway route that passes here. So this is the highway route passing one bridge here, the other bridge here, deep excavation here, another deep excavation here, and very deep excavation also here, and then passing in the tunnel here, going through this hill up to the south. So you see, this is River Bosnia, that is influencing the stability of all this slope, and that's when you look at the morphology of this ground, it is expected that some very slope, creep, sliding could observe at this hill. And here is the layout of the proposed boreholes. So when you have a landslide, you always need to have some cross section, some longitudinal section. In order to define it, you need to have boreholes here, here, and here. So as many boreholes in one typical profile. Also in the longitudinal direction, you need the boreholes to define this potentially sliding area. Here is another example video showing the drilling operation, not exactly here, but 1 kilometer up to the north, where you have some boreholes constructed in the 5 or 6 meter in the soil, and then it passes through rock-like material. Okay. The typical cross section of this cross section B1, B2, B3 is shown here. What is important is that we have a soil-like material in depth of about 20 meters. Down and below, it's found that a very stiff rock, not prone to sliding, is observed at the depths below 20 meters. So when you look at this borehole and the borehole constructed uphill, you can clearly recognize this soil-like material that is potentially unstable. Where is the highway route? It's here. This is the excavation that looks like this. It's up around in total height of around 15 to 20 meters. The groundwater level is observed here. This is this blue line. It's a measured water level indicating that the water collects above this unpermeable bedrock. That's what we explained last time, saying that most of the landslides actually occurred at the contact between the soil and the rock. The rock is usually unpermeable. The water cannot flow down to the rock, so it passes through these contacts and going down to this river at the toe of this potential landslide. So it's very important to have as many boreholes like here, to define a typical cross section. Also to define a longitudinal cross section that will indicate the volume of this potential unstable area. So this was the example of investigation work planned for the highway route passing landslide. So this is that option A we mentioned last time. We need to pass the highway up through the landslide. So we need typical cross section, typical longitudinal section. Similar things uh, happened when we have a landslide activated after highway construction. Here is a typical slope constructed like this in some steps. And here is the sliding that happened after the highway construction. So the highway construction is constructed. It was it was used for 1, 2, 3 years. After that, this failure occurs. Here, what you see, this is gabion walls. This is just a temporary solution that was used. These two rows of gabions and this backfill material just to prevent sliding of the soil on the highway. So the highway was was active, but the reconstruction of this area had to be constructed. So once again, we can apply, we can reach the machine to this hill, and we can perform some boreholes here to define cross section. If we don't have the information from the past when we performed the investigation work for the initial construction of this cut slope. So the original ground surface was like this, the excavation from this side was like this, and from the opposite side like this. If we perform boreholes before, when from here or from here, then maybe we don't need additional information. We just need to do some kind of back analysis to investigate why the failure occurs and to try to design some remediation measure to prevent additional sliding of the ground. Usually, the failures like this happened due to infiltration of surface water. Infiltration of the surface water can is usually the main cause of this so-called shallow top slidings that are 3, 5, or 6 meter deep. But these slopes, these failures can also be can bring a lot of problems to the existing highway route. Another example of a landslide activated after highway construction, but this landslide is also being recognized before highway construction since regional road this past this location. But this is one uh, a bit more serious sliding than this one shown here. If you look deeper in this figure, you'll see some cracks here. You'll also see some cracks over here. So this is direction to the south. This is direction to the north. You can also find these cracks here. You can also find some cracks up here at this regional road. Uphill, we'll show the details later. But here I'll just showing this as an example of possible sliding that can occur after the sliding, and we'll discuss on the possible monitoring and investigation work plan. We'll have uh, all the details of this case study at the end of this first part of presentation, so I'll come back to this landslide activated after highway construction just after I give you some more information about soil samplings and some most usually used monitoring techniques. So if you want to collect samples for some laboratory testings, then these samples are usually collected from the boreholes. So when we are constructing the boreholes, we stop the drilling process and we introduce this so-called split spoon sample. That means when you collect and then this is being pushed to the soil and it's been extracted at the surface, and then you can this is split spoon, so you can overlap it and you can collect your samples. You can protect it by this PVC foil to prevent the natural moisture content of this material, and you can bring the material to the laboratory. Then it will be cut to some smaller pieces and it will be tested in direct shear test, odometer test, anything else you need for the landslide related problems. Most usually we actually need a uh, strength properties, that's cohesion and internal friction angle. When discussing about monitoring techniques in the highway construction in landslide areas, most usually the so-called inclinometers were used to monitoring the movement of the slopes. Here are shown some main elements of this instrument called inclinometer. So what we have, the most important part is this probe, inclinometer probe, that is connected by cable with this readout unit. So we connect the probe to the readout unit by the cable, and what we do, we need to, we are using this probe. We are using this probe to measure the changing of the slope of some initially vertical boreholes. So to perform this inclinometer readings, we need a borehole, and we need this plastic or aluminum pipe with these grooves. So we have a special pipe with the grooves. The grooves are defined so these rollers can fit into these grooves, and we can put this probe down to the bottom of this cased borehole. After we put the probe at the bottom, then we are bringing it up by this cable and measuring any change in the slope of this plastic pipe. So the first thing when installing inclinometers, we need, if we are installing the inclinometers in the ground, we need to drill a borehole. So first we drill a borehole. After that, we put this plastic pipe, plastic or PVC or aluminum pipe, we put it into this borehole. The diameter of this pipe is about 7 centimeters, while the diameter of the borehole is around 20 or 11 centimeters. So we still have some spacing between the pipe and this borehole. That's why we need to do grouting. So we perform the grouting. Water cement mixture is applied to make the good contact of this pipe and surrounding soil. So this is the surrounding soil, this is the PVC pipe, and all around we are performing the grouting. This inclinometer pipe is it doesn't allow the entrance of the material from the bottom, since it's closed at the bottom. It's inserted in this borehole, and here you can see the grouting process. We have this grouting pipe connected to this inclinometer casing, and we fill all this space around the pipe with the water cement mixture. After that, we have to wait for 1 or 2 days so this becomes stiff, all this mixture, and then we can do the initial measurement. First, we always need to perform initial measurement. The initial measurement will define the initial position of this pipe from ground surface to the bottom of this measurement depth. In the future, we can repeat the measurement in 7 days, in 1 month, in 2 months, and we then compare the initial measurements with this new information of this pipe slope. So comparing the measurement on the initial condition and some condition after some sliding occurs, we can see what's the magnitude of the displacement, and more importantly, this is a very important information we get from the inclinometers, that we can get the depth of the sliding area. So here are some additional information on the main principle of this inclinometer. So if this is some initial measurement that we can define as a vertical line, then we have some additional measurement, and we measure by the readout. We measure by the probe, and getting the information on the readout unit that is connected with the probe by a cable. What's the new position of this probe at different depths? This is the borehole, this is this pipe, and these are the grooves, and here is the probe with these rollers. Between the borehole and pipe, we have this backfill material. Usually it's water cement mixture used for grouting. A typical example of inclinometer measurements are shown here, where a relatively deep landslide was observed in different periods, starting from May till April. It's about one year period. That's one example. So what we can see, this is the some vertical line, like initial measurement, and this is the measurement after 1 year period. So what we have by these readings is that we have the magnitude of the horizontal displacements. It's around 2 centimeters or 20 millimeters, and we have the depth of the sliding area. So down below 15 meters, there is no sliding. Up above, we have a sudden increase in the displacement. Very similar results are shown here. But here we have not only the results of the inclinometer measurements, but also the characteristics of the material involved in this location. So this is a very deep borehole that is a 48 meter is drilled at the location. And here we can see that at depth in around 60, 70 meters, also here at 10 meters, and especially here at 2 meters, we have sudden increase in the horizontal displacement, displacement. So what we can see, this indicates some very complex sliding, where more sliding surface occurs. One at the surface, this is the contact from the sole-like material to this fissured soft rock materials, and additional sliding also is introduced here at the 10 meters and here around 16 to 70 meters. So you cannot find nothing special here at this location and this depth, but obviously some sliding was recognized at this depth. The inclinometers are not always installed in soil or rock. It can sometimes be installed in the structure. How do we do that? Well, it can be installed, for example, in piles. When you drill a pile, then after that we are installing the reinforcement cage in this borehole. The reinforcement cage consists of main longitudinal reinforcement and this stirrups reinforcement, spiral stirrups. What we usually do when installing inclinometers in the structures, we put the inclinometer casing along with the reinforcement cage. So we just link it with the reinforcement cage, and then we perform the installation of concrete all around this. So you can see that pipes, this casing, inclinometer casing, remains inside the concrete. After that, we can perform the initial measurement. The initial measurement to define its initial position. The initial position must not be absolutely vertical, but never mind. We have some line that is initial. Any additional change of the slope of this line will define the horizontal displacement. Not only the displacement, but more importantly, the depth of the sliding. The depth of the sliding. Of course, when we have the inclinometer measurement, we always have some point at the bottom that is fixed. Because all the displacement we get by the inclinometer, these are the relative displacements in comparing to this point. And if true displacement goes like this, you'll never get this displacement by inclinometer. You can only get this line. You don't know what the displacement of this bottom point. That's why this point always have to reach some stable area. That's what happened here. Since the expected sliding depth here was expected to be 20, 30 meters, that's why this borehole is so long. Boreholes went deeper and deeper just to be sure that we're going to reach this stable area. So there is no any displacement observed here, and then we recognize some displacement here. That's from the period of March to 18 to August to, so maybe some 6 month period, this increment of 10 millimeters at the top, even even 50, 20 centimeter displacements occurred. The information of sliding depth is one of the most important information parameters when designing highways, structures, highway route in the landslide area. When we have a shallow, small depth landslide, then we don't have a lot of problems. But when we have deep landslides over 10, 15, 20 meters, then the problem becomes much, much more serious, and a lot more energy, money, and technical measured support measure must be performed to prevent any problems on sliding on the structures or highway construction after the construction. One more monitoring equipment that is often used in this relating to the structure constructed in the landslide area is so-called extensometer measurement. Here I show you this so-called extensometer with these magnetic rings. The principle of this extensometer is similar to inclinometers, but the main difference is that it measures not horizontal displacement, so not displacement perpendicular to this pipe, but it measures longitudinal displacement, so the displacement parallel to this pipe. The installation is same as for inclinometer. You must perform a borehole, so you must have some borehole. Doesn't have to be vertical borehole. It can be some slow borehole. Then you have to insert this extensometer pipe that is same as inclinometer pipe. You can see it's PVC pipe. It has grooves inside. It has these couplers, same as inclinometer pipe. But the difference is that it has these magnetic rings at every 1 meter spacing. So we install this casing with these rings spaced on 1 meter. The rings are not fixed to this pipe. It can move. It can move up and down. So we do the grouting around this pipe, same as for inclinometer. We fill all the space between the borehole and this plastic pipe by water cement mixture and grouting this spacing. Then we measure the initial spacing of these rings. It's maybe 1 meter, maybe 99 centimeters, and so on. And after that, if some displacement occurs, then these rings will move. Since the rings move, we have the change of the initial spacing of these rings. The change, so the position of these rings in the boreholes is measured by so-called extensometer probe, similar to this one inclinometer probe. But the inclinometer probe measures the change in the rotation, while this magnetic extensometer measures the change in the spacing of these rings. It's connected by the cable to the readout unit, so we can collect any change in the spacing of the rings. So if we have somewhere located that these spacing between these rings is suddenly changed, that can indicate the location of some higher strain increment, indicating some sliding surface or the depth of the landslide area. Okay, we have some more time before this first link breakage. 7 minutes. I'll spend this time to discuss on the piezometer measurements, on the measurements of the groundwater level and pore pressures in the soil. As we discussed last time, the main trigger of the landslides is the water. So water level increment, pore pressure increment in the soil is the main cause of the landslide, is the main trigger that really pushed the soil to slide down and down the hill. So I'll spend a few slides, 5-10 minutes to discuss on the measuring techniques that are used to observe, to monitoring the water level in the slopes. First, first we'll try to define this term piezometer. Piezometer is one very simple, sometimes more complicated structure construction that is used to measure the groundwater level in the soil or directly to measure pore pressure. For example, if you have a soil profile shown here, it's a sand material, and below the sand it's clay material. Let's say you drill a hole that the depth of the borehole ends in the sand, and the other two boreholes passes the sand and gets down to this clay material. There's three vertical pipes. Let the pipes be perforated at the bottom. Perforated, that means the water can enter this pipe due to this perforation at the bottom. If you measure the water level in the pipes, you'll see that all the levels are same, and it's the same as so-called groundwater level. So this is some free water surface area. In order to indicate the difference between an observation well that is constructed like this is just called observation well, and something that can measure a really poor pressure at one point, and that's the main idea of the piezometer, to measure the pore pressure at one depth. I'll show you this illustration. The illustration consists of the same soil like before. This is original ground surface. This is sand material, and below sand it's clay material. And once again, we built 1, 2, 3, 4 piezometers. One ending here at the sand, the other three passing through the sand and going down to the clay. But the difference between these construction is that this one is perforated at the bottom. This one is perforated by its total length, and these two are perforated only at the bottom. So what happened now, if you applied some fill, some additional load, you apply additional surcharge load at the top of the surface, like some embankment, some platform, to increase the height of this surface, you will see quite a different water level is observed here. First, the groundwater level in these two piezometers is not changing. It's not changing in this one piezometer because this piezometer ends in sand. It's also not changing in this piezometer since this piezometer is perforated through total length of this pipe. But here we have some change in the water level. That's happened because clay material has its characteristics that it's very low permeable. It's very low permeable. It's at a low value of coefficient of permeability, and when you apply additional load, then additional water pressure occurs in this layer. That's called excess pore pressure. It's called excess pore pressure. That's additional pore pressure that is generated in the clay-like materials because the water in the voids actually takes all this surcharge load in the first phase of the construction. And on this kind of a piezometer, you can really measure the total pore pressure at these points. If you use this piezometer too, you will not be able to measure this. That's why this is called observation well. When this water from the sand actually passes down and you have this fixed level here that is different from the true measurements, true information, and that is the total pressure is higher here at some layers of the clay and not here. Excuse me, did you want to ask something? Okay, since we're at the end of this first first part of the lecture, I'll stop sharing and then I'll connect once again to continue. Let's say now it's 14:37. Let's say in 40:45. That's in 8 minutes we can continue.